The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
Hello, my name is Chip Stevens. I'm a philosophy professor here at UC San Diego, and I work on the foundations of quantum mechanics.
Hi, I'm Andrew Friedman. I'm a research scientist at the UCSD Center for Astrophysics and Space Sciences, and I'm an astronomer and a cosmologist by training, but I also work on some experiments that touch on the foundations of quantum mechanics.
Hi, I'm Adam Becker. I am an astrophysicist and a science writer, and I'm the author of the book What is Real? The Unfinished Quest for the Meaning of Quantum Physics, which is about quantum foundations.
So Adam, I met you when we were both graduate students at the University of Michigan,
Yep.
and I know that you've been thinking about these questions for quite a long time.
Yeah.
When did you first encounter these puzzles about the foundations of quantum mechanics, and how did you decide to write a book about it?
You know, that's the short answer is it's been a long process. I read popular science books when I was a kid because I was a nerd, and they always talked about really incredible, strange things happening in physics, usually either quantum physics or relativity. And then when I got a little bit older, I learned relativity because it turns out the math behind special relativity, at least, is high school math. And I learned it, and I thought, oh, okay, now I understand this, and these things that people have been saying that didn't make a lot of sense to me seem a lot more clear. I imagine the same thing will happen with quantum mechanics. I'll learn it in college, and these things that people say about it that don't make a lot of sense to me, like Schrödinger's cat, those things will become a lot more clear once I learn the math. And so I was very excited to learn this when I got to college, especially because I had also heard that by that point I had heard that there was at least one other way of thinking about quantum physics. I had heard of something vaguely called the Copenhagen Interpretation, which seemed to be the standard, and I had heard of the Manyworlds interpretation, and I didn't understand how there could be more than one. And I also didn't understand what was going on, but again, I figured this will all be clear once I learn the math. And then I started learning the math, and I started asking questions, and I actually got in a fight with one of my professors where I asked too many questions about what was happening when we weren't looking. And eventually, with a tone of utter disdain, he said, well, if that's the kind of question you're interested in, then why don't you go to the philosophy department? And so I did. I knew he was, not serious in that suggestion, but I had already started taking philosophy courses because it was something that was interesting to me. And in taking philosophy of science courses as an undergraduate, and then learning more about quantum mechanics and talking with some physicists who were significantly more patient when they think about these questions, like David Mermin, who's one of my professors in undergraduate at Cornell, I came to understand that there was something very strange going on here, that the questions just got worse rather than better as I learned the math, and that there was a very strange history here, and a history that I didn't really understand, and that had led to this strange situation, this kind of asymmetry between physicists and philosophers, where philosophers of physics generally knew quantum mechanics very well, but physicists, even physicists who worked on the foundations of quantum mechanics, didn't always know philosophy terribly well, even when it was very relevant to their work. And by the time I got to graduate school and started hanging out with people in the philosophy department who were doing philosophy of physics, I learned more about philosophy of quantum mechanics, and again, the problems just kind of got worse, and the answers I was getting from the physicists became less and less adequate by and large. And eventually I said, there's a really strange story here, and I'd like to read a book about it, and I can't find a good one. It'd be great if I could write a book about this. Also, it'd be great if I could go to the moon. I don't know how to make either of those things happen. But after finishing my PhD in physics at the University of Michigan, I ended up going into science writing, and through a long and lucky and complicated series of professional moves, I ended up landing with a really great agent, a really great publisher in Basic Books, and my editor, TJ Kelleher. And I was extraordinarily lucky to get a grant from the Alfred P. Sloan Foundation, which enabled me to work on this book full-time for the last couple of years. Quantum mechanics is interesting and worth thinking about because quantum mechanics is the single most powerful theory of physics that we have ever developed. it explains an enormous variety of phenomena, and it does so to an incredible degree of accuracy. I mean, it explains almost all of the technology of the last 100 years. I mean, the LEDs in the screen of your phone and the microchips in your phone and every single computer around, all of those are powered by quantum physics. Quantum physics explains why the sun shines. It also explains why you can see that the sun shines. It explains how your eyes work and how they detect light. It even explains why my feet aren't sinking through the floor right now, because it explains why anything ever remains solid at any time. So yeah, quantum mechanics is the physics of the ultra tiny, but our world is made of ultra tiny things. And so it's really the physics of everyday life as well.
Yeah, and I think that you can make a really good case that quantum physics is by far the most successful theory that humanity has ever produced.
Yep.
Especially in terms of its empirical power, its ability to allow us to predict the behavior of the subatomic world and build these amazing science fiction technologies.
Yep.
I've heard some stats that it would be nice to see if you could verify, but I've heard that something between 30 and 40% of the GDP of the world is ultimately based on technology which is enabled by quantum mechanics.
That sounds about right. Yeah, I've heard that stat as well. I haven't dug into it, but if anything, that sounds a little low.
Yeah, well, yeah. And it depends how you count things, but it also, it's just incredibly interesting in that it's amazing that we can do so much with it, yet as we'll discuss, I'm sure, there's so much that's misunderstood about it.
Yeah.
Despite its being around for nearly a century.
Yeah, that's exactly right.
And I like to start with these misunderstandings when I'm explaining it to people, because I think they're so fascinating that people view quantum mechanics as this completely revolutionary theory. And they have all these ideas about how it's revolutionary. Particles can be in two places at once. What happens next is fundamentally random. Things behave differently when you're watching than when you're not watching. Particles are kind of waves and kind of particles at the same time. There's all these weird aspects of quantum mechanics. And what really fascinates me about it is, does it have to be that weird? Or is there some way to make sense of the theory where we only have a few of those strangenesses and not all of them? That's exactly right. I mean, I completely agree. I mean, the fact that it's weird isn't really a problem per se. I mean, the world is a weird place, and, we need weird theories to understand it, but the question is how weird? Yeah.
And what kinds of weirdness, like you were saying, and also drawing the distinction between a theory that's weird and a theory that may not make sense, that may not be internally logically consistent. You can have the weirdest theory in the world, but if it's internally consistent, then we can start to work with it and see where it takes us. But if we have a theory that actually contradicts itself, then we have a problem, and we need to figure out what's going on, especially if it appears to contradict itself, but it works.
Yeah, and for example, Einstein's theory of special relativity is a prime example of a theory that is weird in the sense that it involves phenomena that are not part of our everyday experience. When you have objects moving at speeds close to the speed of light, you get all these extremely weird phenomenon.
Yeah.
You get time slowing down, and you get the lengths that people would measure changing.
Yeah.
And that's an example where I think we can accept the weirdness because that theory is on much more solid ground in terms of it being internally consistent.
Yes.
Both its predictions and its explanatory power fit together nicely.
Yes.
And that so that quantum mechanics, as Chip was saying, there may be some weird elements to it that we just eventually have to accept. But despite what many in the community think, it's not a slam dunk case that we just simply have to accept these ideas that are often, in popular culture talked about in terms of, well, electrons can be in two places at once. That actually is not exactly a settled point.
Yeah, no, that's exactly right. Yeah, and the other reason why I think special relativity is a really good example is it's a theory which, when you first look at it, appears to have contradictions. The famous one of the famous things about it is that you've got time slowing down as you go faster. But one of the things that looks really weird about it is when I go faster, you would say that my time is slowed down, but I would say that your time is slowed down as well. And that appears to be a contradiction, but it turns out that the theory has a very nice way of handling that situation such that it's not actually a contradiction, and it's dealt with in a very explicit way. Quantum mechanics doesn't always meet that same standard.
Yeah, so one other problem that comes up when people try to face the contradictions of quantum mechanics is to be kind of quiet about quantum mechanics, or to be a bit not telling a full story about what's actually happening.
Or
And so-
shutting up and calculating.
Yeah, shutting up and calculating, right? So one way in which a version of quantum mechanics or a way of approaching quantum mechanics can be unsatisfactory is if it has inconsistencies.
Yeah.
Another one, as we said, is if it's weird, but maybe
Yeah.
that's not so bad.
Right.
And then another problem is if it's kind of incomplete. It tells some story of what's happening, but it doesn't really tell you what's going on.
Exactly. Yeah. No, that's exactly it. Yeah. And I think that's a lot of where the disagreements about quantum physics and its history sort of got started.
Could you tell us more about that?
Yeah, absolutely. So, quantum physics was something that was put together over the course of the first quarter of the 20th century by some of the most brilliant physicists the world has ever seen. But it was really a team effort, and it wasn't an especially well coordinated team effort. It's not like there was a leader of the team. The closest thing that the team had to a leader was the Danish physicist Niels Bohr. And Bohr's Institute in Copenhagen became the center of activity for the physicists developing quantum physics. And it was out of that institute that this set of ideas about how to think about quantum physics, let me back up a moment. The first full theories of quantum physics really showed up in about 1925. And that's when we went from having this incomplete understanding of how to even predict what was happening in the quantum world to having a full theory that really let us predict almost whatever we want. And it was just not immediately clear how to interpret that theory because it doesn't really look like the world around us. And the first set of ideas about how to do that came out of Bohr's Institute in Copenhagen and became known as the Copenhagen Interpretation. The problem is that the Copenhagen Interpretation, by and large, looks at the strangeness of quantum physics and says, look, this is irreducibly weird, and we aren't going to theorize about what story of the world could possibly lead to such an unusual theory. We're just going to say that's not the kind of question that you should ask. And that's an oversimplification, or no, it's a simplification. I wouldn't say it's an oversimplification. I think it's a fair characterization. People would disagree with me, but whatever.
So following up on that, it definitely seems to me, at least in my education in physics, that many people are just content to say, well, quantum mechanics is incredibly empirically successful.
Yep.
Look at all the gadgets that it's enabled us to build.
Yep.
It obviously works. Why bother trying to understand what's going on under the hood? These are just a set of mathematical tools we can use, and that they're very convenient. We don't need to, over philosophize or over interpret this stuff. So, why, in your opinion, do we actually really need an interpretation?
Yeah, that's a great question. So, let me back up a moment, and then I'll answer that question, and just talk a little bit about why we even talk about an interpretation in the first place. Because we don't talk about an interpretation of, say, Newtonian physics, right? The classical physics of Isaac Newton from the 1600s. But the reason we don't really generally talk about that is that it doesn't seem like something we need. So if I want to describe where, for example, my cell phone is. If I want to describe where my cell phone is, in Newton's physics, I just need 3 numbers to do that. I can just say, okay, it's this height above the floor, it's, 2 feet to the left of me and 1 foot in front of me or something like that, and that's 3 numbers. In quantum physics, if I want to describe where a single object is, even something much simpler than a cell phone, like an electron, I need an infinity of numbers scattered across the entire universe. And that infinity of numbers is called a wave function. And the wave function behaves in some very unusual ways. And that is, it's not immediately clear how that lines up with the world around us. And so finding a way to interpret the odd mathematical things in the theory is necessary in order to even tell what the theory is saying about the world around us. And wave functions aren't just weird because they seem unfamiliar. They also have this strange set of behavior. Most of the time they obey something called the Schrödinger equation, which is a beautiful equation at the heart of quantum mechanics that says that wave functions basically wave, that they undulate and generally move about smoothly and don't change too suddenly. But then every so often they don't obey the Schrödinger equation. When we actually look for the thing that is associated with the wave function, when we look for that electron, the wave function suddenly stops obeying the Schrödinger equation and collapses. All those numbers across space become zero everywhere except for where you look for the electron. That's a problem. That's very weird. It's very strange to find that what appears to be a law of physics, the Schrödinger equation, seems to get suspended sometimes. And also the times when it gets suspended are times when we make measurements, and the idea of measurement is not something that's terribly well defined. It's hard to pin down exactly what a measurement is. Albert Einstein once asked, does the universe change when a mouse measures a wave function? Does that count? Another physicist called John Bell said, did the wave function of the universe have to wait around for a bacterium to appear, or did it need a better qualified observer, like somebody with a PhD? That just doesn't seem to be the way the universe could work.
I think it requires Mickey Mouse with a PhD.
Yeah, that's right. It requires Mickey Mouse with a PhD. Yeah, so there's a problem here. Even if that is how the universe works, we need to have a better understanding of what it means when we say measurement. So there's two questions here. The first is, there's two reasons why we need an interpretation. The first is we need an answer to this thing about measurement. This is called the measurement problem. We need an answer to the measurement problem. And we need some kind of interpretation in order to guide our usage of the theory at all. Because we need to know when the Schrödinger equation applies and when it doesn't. The other reason I think we need an interpretation is precisely because the theory works so well. The theory works astonishingly well. It describes so much of the world around us. It gives us such accurate predictions. It has to be hooking onto some real feature of the world that is at least approximately similar to what it describes in the theory. There must be some relationship with something in the world that is reasonably well described by the mathematics of quantum physics. Otherwise, why would the theory work at all? And it does work. It works phenomenally well, especially when you remember that the theory was originally put together to describe a really small category of phenomena. It was just put together to describe these things called spectral lines, which is basically what happens when you hold up a prism to a bottle full of gas when you heat up the gas. Because when you hold up a prism to like a bottle full of glowing gas, you get some bright lines instead of a full spectrum, like instead of a rainbow. Explaining the appearance of those lines and the way that they behave was why quantum mechanics was first put together, and then it turns out it explains almost everything else as well. So there's something funny going on there, and without a better understanding of how quantum mechanics is related to the world around us, I don't think we stand much of a chance of finding a better theory. So that's an extremely long-winded answer to your question.
Yeah, and the way Andy asked the question, it was similar to a quote you had from Bohr in the book, where Bohr said, look, I'm not trying to understand what's actually going on in nature. I have a theory that's going to tell you what you'll see when you look, but it's not a theory that really describes nature. Right. And that seems incredibly radical to me, right? Yeah. You would have thought the point of physics, why we do physics, is to understand the laws of nature that govern our world, and understand what stuff is governed by those laws. Yeah. That's why I went into physics, right? Yeah. Like, that's what I cared about. I wanted to answer those questions. And when I came to quantum mechanics, I felt like the physicists had just given up. Yeah. The way they explained it to me, they're like, yeah, it's actually really hard to tell what's actually going on in nature. We don't have a good theory for that, but we do have a theory that'll tell you what you'll observe. Yeah. And, you should be happy with that. And I wasn't happy with that. Yeah, no, nor was I. I mean, and you're in good company. I mean, this is what you just said is very similar to something that Einstein said. Einstein said that he thought that the point of physics was to understand the physical world around us, regardless of whether or not somebody was looking. And by that he didn't mean that the act of observation couldn't somehow affect the world around us in some subtle ways. But he did mean that there is a world that exists whether or not we're looking at it, and the point of physics is to understand what is happening in that world. Yeah, good. So you sort of set up this debate between Niels Bohr and Albert Einstein, right? Yeah. They had different ideas about how to understand quantum mechanics, and you have a chapter entitled Street Brawl, Street Brawl, where you talk about the debate between them. How did that go in practice? What happened?
Yeah, what happened in that debate, and this is, a summary, but what happened in that debate is that Albert Einstein and Niels Bohr debated quantum physics and the nature of reality, and Einstein had much better arguments and reasoning on his side, and he won the debate, and Niels Bohr lost, but Niels Bohr's views carried the day anyway, and people felt that Bohr had won, even though by and large he had given completely inadequate responses to what Einstein had said, and in many cases completely misunderstood what Einstein had said.
For all of Bohr's, incredible achievements, a Nobel Prize winner, his model of the hydrogen atom was crucial to the development of quantum mechanics, amongst other things.
Yeah, Niels Bohr was an incredible physicist. He was an amazing physicist. His model of the hydrogen atom was amazing. It led to quantum mechanics as we know it. He also was among the first to understand exactly how uranium fission worked, which is a very important process. He was a very, very good physicist. Yeah.
So this is not at all to denigrate his major accomplishments,
Yeah.
but in my experience, whenever I read a quote from him in these debates, it kind of goes off the rails in terms of using unintelligibility as kind of an escape route from careful scrutiny. So that his quotes can be interpreted in so many ways that on the one hand, some people can just sort of say, well, if I trust him, then there must be some hidden knowledge in there that would if only I had his intellect, I would understand quantum mechanics. But Einstein wasn't buying it.
Yeah, that's right. Yeah, I think that's exactly right. Bohr was not the clearest writer at all by a long shot. He was also apparently not much clearer in speaking. He was not the best at giving speeches or talks. He was sort of famously obscure, and I think that your characterization of what people took away from that is exactly right, that obscurity actually worked to his advantage in these debates, and that what Einstein was saying was extremely clear, because Einstein was very good at writing and speaking. And so Einstein presented these extremely clear and straightforward and seemingly simple examples, because Einstein was very good at distilling his points down to the simplest possible examples in order to make them easier to understand. And then Bohr would reply with a stream of overwrought and nearly unintelligible prose or speech, and then would walk away convinced that he had won. And this gave the impression to many of the people around him that Bohr was right and Einstein was wrong, especially because Bohr was arguing for the completeness of a theory that manifestly worked. And Einstein was not arguing that quantum mechanics was wrong, he was merely arguing that the job wasn't finished. That just because it's right doesn't mean it's done. And that was an uncomfortable prospect for a lot of people. And so the fact that Einstein was arguing for an uncomfortable point, and that an uncomfortable and unpopular point, and that Bohr's replies were, let's say, Baroque enough that anybody could find whatever they wanted in there and interpret it however they wanted, and that Bohr was arguing for a position that was much more popular, the conclusion was that Bohr had won.
Yeah.
Even though he did not.
And I can understand how it would have been seen as more popular, because in a way his position was saying everything's okay. We got this covered. Don't worry about it. It's I know it seems complicated, but it'll all work out in the end.
Yeah.
And it also seems to me a really interesting example in the history of science where human cognitive biases and the way that humans operate emotionally, more than rationally in many contexts, kind of carried the day. My understanding is that Bohr was a very, very powerful and charismatic figure,
yes,
both in terms of his institutional power in Denmark, and he's the kind of a guy that would end up on coins and dollars.
Yeah, exactly.
And then Einstein's views, even though they might have been more articulate, there were certain assumptions that Einstein made that people could clearly point to what they were, and maybe just subjectively they disagree with those assumptions, and then they could say, all right, I feel pretty good. But with Bohr, they couldn't even figure out what the assumptions were, so there was nowhere to attack.
No, I think that that's all exactly correct, and the idea that Bohr's position was very comforting is actually one of the things that Einstein attacked. Einstein called it a tranquilizing philosophy, and then complained that it had very little effect on him.
Yeah. So the way we've painted things here, we've got Bohr saying that everything's basically okay.
Yep.
And then Einstein saying, no, it's really not.
Yeah.
And your book begins with that and then goes on to tell the story of some of the people who thought everything was not okay.
Yeah.
So you get into some of the people who really had problems with the way that quantum mechanics was standardly understood.
Yeah.
And then tried to do better.
Yeah.
And one of those people is David Bohm, right?
Yes.
So David Bohm initially found the tranquilizing philosophy somewhat acceptable, right? So he
Yeah.
wrote a book on quantum mechanics where he put forward a version of Bohr's interpretation of quantum mechanics.
That's right, yeah.
But then he had a meeting with Einstein that
Yes.
sort of led him down a different path. Can you tell us about that?
Yeah. So David Bohm definitely followed in the footsteps of Einstein in that he did not think that everything was okay. And he paid a price for that and for other things. He had a very interesting life. So David Bohm, as you said, he thought that everything was okay for a while. He wrote a textbook on quantum mechanics that was sort of espousing what he thought Niels Bohr's view was, what he thought the Copenhagen interpretation was. But as he was writing it, doubts started creeping in. He by the time he was done writing it, he said he wasn't sure he fully understood it. And he was no longer sure of himself. And then the book came out, and Einstein called, because at the time Bohm was in Princeton where Einstein was, and Einstein called and said, I'd like to see you and talk with you about your book. And so Bohm went and spoke with Einstein and basically confessed, I'm no longer sure that I agree with the position that I put forward in this book. And Einstein said something to the effect of, you've given it the best defense it could be given, and the only reason you're still not convinced is because this position is indefensible. Quantum mechanics isn't done. There's something missing. The story's not over yet. We need to think about this more clearly, and we probably need a new theory. And Bohm really took a lot of inspiration from that, and he left that meeting, he said, just with one thought ringing around his head. He said he was thinking about, could he find another way of looking at quantum physics? And at the time, he was going through a lot of personal turmoil. He was actually waiting for his day in court. He had been arrested on charges of contempt of Congress shortly before his book came out because he had been hauled up in front of the House Un-American Activities Committee and asked to name names, for other people who had been members of the Communist Party, because this was the early 1950s, and Bohm had briefly been a member of the Communist Party. And he didn't name names. He pled the Fifth Amendment, and so he was arrested, and then he was out on bail waiting for his day in court when his book came out, when Einstein called, and facing down some serious jail time. And while he was waiting for that, he sat around and thought about other ways to think about quantum physics, and he found one within a couple of months. He actually rediscovered independently some ideas that had been first put together about a quarter century earlier by one of the founding fathers of quantum mechanics, Louis de Broglie, and then extended those ideas and sort of completed the theory. And in Bohm's version of quantum mechanics, there's not these weird questions about, is there a particle, is there a wave? Instead, there's particles guided by waves.
Right.
And these pilot waves that guide the particles around can lead the particles on counterintuitive paths that lead to these strange phenomena that we see in quantum physics, and they have some other very strange properties, but particles are not in more than one place at once, and more importantly, there's a clear idea of what's actually happening in the theory, and measurement doesn't play any special role, and so these thorny questions about measurement don't have to be, they get good, concrete, solid answers, and we don't have to worry about, is the theory consistent?
Yeah, I think this is a really nice aspect of Bohm's theory.
Yeah.
Because before we said, well, we've got this wave function, and the wave function behaves in a wavy, undulating way. When you're not looking, it obeys the Schrodinger equation. But then when you do look, it collapses, it jumps to attention, and it acts more like a particle, right?
Yeah.
So it's acting sometimes like a wave, sometimes like a particle.
Yeah, exactly.
On Bohm's theory, there just are both things. There are
Yep.
waves, there are particles. The waves always behave like waves. So the quantum wave function obeys Schrodinger's equation all the time. There's
Yep.
no, wait, a measurement's going on, do something else. No,
Yep.
it's always the Schrodinger equation, and the particle always behaves like a particle.
Yeah.
The particle obeys its own equation. It's a new equation. It's
Yep.
not part of ordinary quantum mechanics. So Bohm's theory is mathematically different than ordinary quantum mechanics. It has its own new physics to it, new laws of nature.
Yes.
But from that, you're able to avoid this strangeness, and yet it hasn't really caught on for some reason.
Yeah. I mean, despite the fact that it has that new law in it describing how the particles move, it does perfectly reproduce all of the predictions of standard quantum mechanics. And so in that sense, it sort of partakes in the success of quantum mechanics. And given that, it is surprising that it didn't really catch on more than it did. But part of the reason is what was going on with Bohm, because he sent off these papers to be published. He had his day in court. He was cleared on all charges because, as it turns out, there is a Fifth Amendment to the United States Constitution. But then he was blacklisted. He had recommendation letters from Einstein and from Robert Oppenheimer, the father of the atomic bomb and Bohm's former PhD advisor. But even with those incredible recommendation letters, he couldn't get a job anywhere in the U.S. He ended up in exile in Brazil. The U.S. consulate confiscated his passport, so he was trapped in Brazil illegally. And ultimately that meant that he was unable to defend his theory with a series of talks and meetings and conversations when his papers were published. And they weren't completely ignored, but the voices of the older generation who had put together quantum physics and who were mostly still around were just louder than Bohm's, because Bohm was stuck in Brazil and he was only one person. And ultimately, his ideas were largely ignored and forgotten.
This is a very interesting example, in the history of science of how war and how politics ultimately end up, these are not scientific pursuits in and of themselves, but they can end up dramatically dictating the probability that a certain theory will end up winning the day. And it's really, really interesting because, if history had been different, we can imagine sci-fi scenarios where certain things had been discovered first. I mean, Louis de Broglie might have discovered Bohmian mechanics had he been encouraged in certain directions in a different way. And then, we might be today stumbling upon this new amazing Copenhagen interpretation as an advance where we don't have to worry about any of this stuff anymore, But it certainly proved Bohmian mechanics, whether or not you are a proponent, that there is more than one way, of baking the cake, and that there's more than one way of telling a story about what's happening.
Yeah, that's right. I mean, although I would argue that the Copenhagen interpretation doesn't really tell a story about what's happening. So you could argue that really what was going on with Bohmian mechanics was it was found that there was a way to tell a story about what was happening.
Well, I agree with you up to a point. If I was going to tell a story about the Copenhagen interpretation, I would say that when particles are not being observed, they exist in a superposition of many different possible states, and the wave function, all it can tell you is the probability that you'll find a particle in a certain place, but it's meaningless to ask questions about where it really is until you make a measurement. Everything obeys the Schrodinger equation up until that point, and then magically, once you decide to make a measurement, however that's defined, suddenly the universe stops obeying the Schrodinger equation, and reality snaps into place. Now that's not necessarily a good story, but I still think it's a story.
I will grant you that is a story that has questionable logical coherence.
I would agree with that as well.
Yeah, that it is
stories themselves are just that. Stories are not necessarily logically consistent by themselves.
That's true.
Mathematical theories themselves, if they're not logically consistent, then they don't even have a foot to stand on.
Sure, yeah, but it's that story that you just spun of the Copenhagen interpretation. While I agree it is a fairly accurate representation of what it says, it is unclear what that story is saying and whether it really holds together.
And I think we should be careful to distinguish two ways of understanding the Copenhagen interpretation here that are quite different.
Yes.
So one big difference that there is it the case that when a human being observes a quantum system, they cause the wave function of that system to collapse? Is there some role for consciousness here relating to the collapse of the wave function? Or is it just a theory that only tells us about what we see, a kind of instrumentalist theory that doesn't tell you what's really happening in nature, but only gives you probabilities for what you'll observe? And so in that case, it's just kind of quiet about what's really going on, and Bohmian mechanics is a way of filling in the details. And so the way Andy told the story before, well, maybe if you had Bohmian mechanics first and Copenhagen second, Copenhagen would look like an advance. I think it would look much more like a step back. I think if people had Bohmian mechanics on hand, they'd say, look, I have a way of understanding what's really going on in nature. I've got laws here. I don't need to suspend them at any point. I don't need to say that this doesn't tell me what's really happening. It gives a real account of what's happening. And Copenhagen, I think, would look like a step back relative to that.
I agree it would look like a step back.
Yeah.
But, you know, in a hypothetical science fiction world, who knows what voices would be the loudest and who would carry the day.
That's certainly true.
That's all I'm saying. It might be the most popular for whatever reason, even if itself is not a very, very good idea.
So science fiction allows us to transition into a third way of looking at quantum mechanics, right?
Yes, it does.
We had first the Copenhagen interpretation. Then Bohm, inspired by Einstein's criticism of his way of looking at it, came up with Bohmian mechanics.
Otherwise known as pilot wave theory.
Or pilot wave theory, de Broglie-Bohm pilot wave theory.
It goes by a lot
number of names. Sure. And then we have this young science fiction aficionado, paradox lover, Hugh Everett, and he comes up with a third interpretation. Tell us about that.
So Hugh Everett definitely came up with the most science fiction sounding interpretation of quantum mechanics, far and away. He looked at the problems of quantum mechanics and he said, he agreed with Einstein, we're not done here. There's a problem. We need a more complete understanding here. And he looked at all of this and he said, what if the Schrödinger equation just applies at all times and that's it? And from that, he figured he could just get a picture of the world, and the picture of the world that he found when he tried to do that was this idea that instead of there being just one universe, he found a multitude of universes continually splitting off from each other, and this is known as the Manyworlds interpretation of quantum mechanics. And so there the idea is, when wave functions always obey the Schrödinger equation, and when you look, nothing particularly special happens. When you look, you split as well. Like, you see a wave function for a particle that's in two different places, and then when you look, there are two copies of you, and one of you sees the particle in one place, and the other one sees the particle in the other place. And that is what Hugh Everett put together, and it definitely sounded like something he saw in his science fiction magazines, and I think that's one of the things he liked about it. And in fact, it was ultimately discussed in science fiction magazines, which made him really happy.
That's funny. So it sounds like when you hear that, like it can't be right? This idea that I'm branching, wait, I don't seem to be branching. And Bryce DeWitt had that criticism that he gave to Everett. He said, wait, no, I don't see myself branching. This theory can't be right. But Everett had a great response.
Yes, he did. Oh, God, I love this. No, I'm so glad you asked this. So Bryce DeWitt was a great physicist who heard about Everett's theory back when Everett first came up with it in 1957. And he was very skeptical. And he wrote to Everett saying, look, you say that the world splits and we split with it. I can just tell you from my personal experience, I don't appear to have ever split into two copies. So, doesn't that mean that your theory is wrong? Everett wrote back saying, look, when people first proposed that maybe the Earth was not at the center of the universe and that the sun was at the center of the solar system and the Earth went around it, people said, well, look, that has to be wrong. Because if that's true, the Earth rotates once a day. And we know that the Earth is pretty big, so that means the Earth is moving phenomenally fast. And when you spin something fast, things fly off of it. Like if I spin a wet basketball, droplets will go flying off in all directions. We don't fly off the surface of the Earth, so therefore the Earth can't be rotating and it must be at the center of the universe. And Everett pointed out, this seemed like a reasonable objection, until we had a theory that not just accounted for how the sun could be at the center of the solar system and the planets could be going around it, but also accounted for our experience of not feeling like we're being thrown off the Earth. In other words, a theory that involves a notion of gravity, a force of gravity that keeps us attached firmly to the Earth. Similarly, Everett said, his theory did involve people branching, but it involved people not feeling like they were splitting. If you ask any one copy of a person in Everett's Many Worlds interpretation, how many copies of yourself do you see? Everyone will always say, just one. There's only one of me. What are you talking about? So he said, if you think that you can just look at yourself and say, I don't split, and therefore your theory is wrong, I have to ask you, can you feel the motion of the Earth? It doesn't mean it's not moving. It just means that there's some theory that accounts for why you can't feel it move.
Yeah, I think that's really interesting because, Galileo considered a lot of those arguments in his dialogue on the two chief world systems, right?
Yes.
So he had these arguments, if the Earth was spinning, it would be like a potter's wheel and you'd be flung off like little bits of clay. And then he felt he had to respond to those in order to defend his Copernican theory that the sun is at the center of the solar system and not the Earth. But another interesting thing that was going on in that dialogue of the two chief world systems is that Galileo said, look, the main kind of arguments I'm going to give you in favor of my theory are not that it's empirically way better than the alternative, that the Earth is at the center of the cosmos. I'm not going to argue that there's some definitive experiment you can conduct that'll show that my theory is right. Instead, he just wanted to say, look, they both can account for the data. Both of these theories would predict the same observations. What we see is consistent with both of them. And then argued that my theory is certain virtues, there's certain reasons why this is a nicer theory, it's a better theory.
Yeah.
So in particular, Galileo had a cute example where he said, look, if the Earth was still and everything else was rotating, then the stars so far away from us would have to be rotating really fast around the Earth. Mm-hmm. And that just seems so implausible. It sort of makes more sense to think it's the Earth that's rotating and not all the stars. Then you can hold all the stars fixed and they don't have to be rotating. So he gave these reasons to think it's a sort of more plausible theory. And if it's able to account for the evidence, you should believe it. And I think Everett had similar ideas about his theory, right?
Yes, he did,
so, this theory can account for the evidence, and it's more elegant than a theory in which consciousness causes collapse or something like that. It's a sort of better theory.
This brings home the point that for theories, you can talk about the predictive power of the theory, and then you can talk about does its predictions match observations, and then you can talk about the explanatory power of a theory. Does it tell a coherent story, and that. This kind of goes back to this question of why we need an interpretation of quantum mechanics, and that at the very least, it is well understood today that there are many possible explanatory versions of interpretations of quantum mechanics, and that some of them have in certain people's minds certain subjective virtues, but one would hope that there ultimately are interpretations that are more and more correct, more and more actually telling a story about the real world. And right now, as far as I understand it, most of the quantum interpretations, with a few exceptions, if they don't actually modify the equations in a mathematically meaningful way, they all give the same predictions. And that those that do modify the equations can give slightly different predictions. So, that would be an interesting tiebreaker. And that ultimately, I think, a reason to come up with interpretations is to guide this question of how do we modify the theory to make new predictions, which would allow us to understand that next step in physics.
Yeah, I mean, this is very similar to something that Richard Feynman once said. He pointed out in a series of lectures at Cornell that got compiled into a book called The Character of Physical Law. He pointed out, you can have two completely identical theories in terms of what they predict and the mathematics behind them, but they can be interpreted in entirely different ways, like a theory with the Earth at the center of the universe and a theory with the sun at the center of the universe. They both predict the motion of lights across the sky in identical ways, but they are going to lead to very different ideas about how to modify those theories to account for new information, how to what experiments to conduct and how to conduct them, and what things in the world are physically possible. And they also change the way that we look at the culture around us. I mean, the idea that the Earth is not at the center of the universe was a profound shift in the way that humanity thought, and it led to all kinds of other advances. Some of them were scientific, some of them were just changes in culture and art and politics and every other sphere of human endeavor. I mean, ultimately, at the end of the day, you could come up with an infinite number of different stories to go with one set of, mathematical laws that match the observations that we see, but which one you pick really affects where you go from there and what theories you end up finding, and helps you find the next theory that will do an even better job.
And this was a major motivation for me going into quantum foundations, exactly this argument about why it might matter. So of course, on the one hand, I was just curious, this fundamental question of physics we talked about earlier, what is there and what does it do?
Yeah.
What stuff is in nature and what are the laws that govern it? I mean, I was curious about that, and that's why I wanted to do physics, and I felt like trying to figure out the right interpretation of quantum mechanics, trying to understand the foundations of quantum mechanics was one way to answer that question.
Yeah.
That was part of the motivation. But if I felt like all we'd ever be doing is just putting forward ideas that we could never test and that it wouldn't really progress physics in any way, it'd be great to have these options, but if we were just going to have a larger and larger array of options, it wouldn't quite feel so important. But part of what makes it feel so important is when you have these options, and these options that aren't just stories, but they're different, mathematical laws, then it gives you options about what to change for the new theory. You can tweak this over here, tweak that over there. You have ways to develop new physics sort of pointed out to you by these different interpretations of quantum mechanics. And I think, to me, that's where I feel the real value is in this current work in quantum foundations. Figure out what are the options that really work, how should we understand those options, lay them out, and then we'll let the future of physics decide which one is right.
Yeah, and science doesn't operate in a vacuum, in the sense of if you're trying to decide what experiment should I perform next, or what research program should I pursue next, that in itself is not a purely scientific question.
That's right.
It has an interplay with all sorts of cultural and political, economic forces, and that when you have a certain interpretation, it can dramatically inform how you make those choices. And so it's broadly part of science as a cultural practice and as an institution, made up of humans, operating not always rationally, but with their own interests and their own motivations. But the point is that if you have an interpretation which is clearly awful, you can end up sending an entire field down a rabbit hole. That in hindsight people would look back on and say, there's no way that this was ever going to produce anything interesting about the world. We're not going to learn anything. We'll learn less about the world if we have a bad interpretation. And unfortunately, the Copenhagen interpretation, as it stands, is an interpretation which not only invites that kind of a problem, it invites you to not ask questions at all.
Yes, and that's a really frustrating thing about it. And yet it has been propped up by exactly the sort of non-scientific forces that you were talking about. I mean, the complex history and cultural and economic forces throughout the course of the 20th century have really, for the most part, up until the end of that century, really benefited the Copenhagen interpretation. Nothing more than World War II, really. World War II was really an enormous boon to the Copenhagen interpretation in a lot of ways. I mean, the theory is strange, quantum physics, and you want to ask questions about it, but World War II dramatically ballooned the size of physics classrooms because of the amount of money that was pouring into physics in the wake of the Manhattan Project, the development of the atomic bomb. And so with the larger classroom sizes, physicists found it much more difficult to talk about these foundational issues, which made saying, we don't have to worry about them at all, just a much more logistically easier position to take. And the money that was pouring in from the military, and I mean a lot of money pouring in from the military, it was something like 96% of all U.S. physics research within 5 years of World War II, by 1950, something like 96% of all physics research in the U.S. was being funded by the military or by organizations, that were essentially associated with or part of the military. And that persisted for a very long time, and those military and government streams of funding were really very interested in finding applications for quantum physics, because the last application for quantum physics that was salient in their minds was the atomic bomb, and then the hydrogen bomb, and then the nuclear submarine, and radar, and all of these other, advances in technology that had tremendous military use. And so that really directed where physics went for much of the middle third of the 20th century. And the Copenhagen Interpretation said, yeah, there are really difficult questions at the core here of this theory. Don't worry about them. Shut up and calculate. Get the job done. Build the submarine.
So another person who was ultimately not interested as much in the shut up and calculate approach, that really took seriously the idea that, well, maybe thinking about foundations could actually lead to new experiments that could test models of reality, was John Bell.
Yes.
And Bell's theorem from 1964, I believe, was what you call in the book one of the most important discoveries in all of science.
Yeah.
Do you want to talk about that a little bit?
Yeah, absolutely. Yeah, no, I think the physicist Henry Stapp said that Bell's theorem was the most profound discovery in all of science. I think that might be overstating it, but the fact that I can't categorically say that's an overstatement says something. I definitely think it was the most profound insight into the nature of reality since Einstein. I don't think there's really a lot to compete with that. But yeah, Bell was definitely not happy to shut up and calculate. Bell got into arguments with his teachers in school. He grew up in Belfast, in Northern Ireland, and he was extremely frustrated with what he saw as the vagueness at the heart of quantum physics. He went and read Bohr and other founders of quantum physics like Heisenberg, didn't find anything more clear there. And then in 1952, he saw the papers that David Bohm wrote about pilot wave theory. And he had been told that doing something like that was, proven to be impossible, and then he saw these papers that Bohm wrote that were clearly a very reasonable way of thinking about quantum mechanics, and he said he saw the impossible done, and that cemented it in his mind. He said, okay, I'm definitely taking a closer look at this. I need to understand this. I don't have time to do it right now, because at the time he was working for the Atomic Energy Institute in the UK, doing work on particle accelerators, but he was determined to come back to it and figure out what was going on and why people thought it was impossible. And so then finally, in the early 1960s, he had some time on his hands to do that, and what he discovered was that there was something very, very odd at the heart of quantum physics. That quantum physics has to be describing some fundamental reality that is much, much different from the way that we think about the world, and that there are some really big questions that need to be answered, and that in a lot of ways, the problems that Einstein flagged up about quantum physics in his arguments with Bohr were exactly the questions that needed to be answered about quantum physics. So specifically, Bell started looking at a really unusual feature of Bohm's interpretation. After he had sort of, he took that proof that people had said, proof that Bohm couldn't be right. He took that and just kind of deconstructed it. He disassembled it and kicked it to the curb. And then after that, he said, okay, so now that we know that theories like Bohm's are perfectly reasonable, what about the strangest feature of Bohm's theory? Because it turns out the strangest feature of Bohm's theory is not that you have both particles and waves. The strangest feature of Bohm's theory is that the position of one far distant particle can affect the pilot wave of another particle instantaneously, faster than the speed of light. And that's very strange. Directly contradicts special relativity, or at least it seems to, and it's just profoundly weird. It's the kind of thing that Einstein was very uncomfortable with. And Bell wanted to see if there was a way to come up with something like Bohm's theory, but without that. And so he started looking at quantum physics to see if there was a way to do it, and he couldn't find a way to do it. And eventually he proved that it couldn't be done. He proved that quantum physics has to have these sort of instantaneous long-distance connections. Hold on, I need to go back and edit that. What he proved was that if you conduct a particular experiment and the outcome of that experiment is consistent with what quantum physics says the outcome of that experiment should be, in other words, if quantum physics is correct in its predictions for all experiments of this type, then there must be something, there must be some sort of instantaneous long-distance connections in the world, or something even stranger is going on, like Everett's Manyworlds interpretation. That is what Bell proved, and it was very, very odd. And he published it to a resounding silence. Nobody even, corresponded with him about it for almost 5 years, despite the fact that it was so profoundly interesting.
Yeah, one of the other ways that I've understood Bell's results, he was very interested in thinking about a worldview similar to more what Einstein was interested in.
Yeah.
And so, he had several different versions of his theorem, and that there are different assumptions one can make to derive the theorem.
Mm-hmm.
But the thing that I've always found really interesting is that if you start with Bell's assumptions, which are eminently reasonable assumptions about the world,
Yep.
They can include things like there is an external reality that exists independent of observation. Particles have definite properties independent of whether we measure them. He also wanted to assume that the principle of locality, the idea that if two distant systems no longer interact, something you do to one system, can't affect something very, very far away. Yeah, and that another assumption is that when we're deciding how to do our experiments, we're perfectly free to choose how we do our measurements.
Yeah.
And the interesting thing is that if you logically follow those assumptions to their conclusions, what you show is that if the world was based on those assumptions, then it would make predictions for certain experiments that are in contradiction with what quantum mechanics predicts and with what we see in these experiments, specifically with entangled particles.
Yeah.
And so this is just a really stark example of how thinking about interpretations leads to, experiments that one can do, and in fact have become a cottage industry now.
Yep.
That are the basis of all sorts of new, amazing technologies that rely on so-called quantum entanglement.
That's right. Yeah, and that happened because Bell, bothered to look into this, and that happened because Bohm published his theory. So without David Bohm and then John Bell after him, we wouldn't have this entire discipline of quantum information theory.
Yeah. And interestingly, we can follow it back even further. As Andy mentioned, understanding entanglement here has proved to be really interesting.
Yes.
But in the first place, when entanglement was first understood to be part of quantum mechanics, came from thinking of the foundations of quantum mechanics.
Mm-hmm.
So it came from Einstein's EPR paper.
Yes.
And then the way Schrödinger reacted to that, right? Can
Yeah,
you tell us about that story?
Yeah, absolutely. So.
And do you want to define entanglement a little more for
the
listeners?
So entanglement. The simplest definition of entanglement I know, entanglement is what happens when two particles interact in quantum physics, and that's pretty much it. Almost any time two particles interact in quantum physics, they become entangled, and what that means in practical terms in the mathematics of quantum physics is that those two particles no longer have individual wave functions, they share a wave function. And that means that something you do to one of them can instantaneously affect the other one, or so it seems, at least. And Einstein was profoundly disturbed by this. He pointed this out in a paper called the EPR paper, which was named that way because he did it with two other people, Podolsky and Rosen. So EPR is Einstein, Podolsky, and Rosen. He published this paper in 1935 saying that quantum physics clearly wasn't complete, because if it was complete, it could lead to these long-distance connections, and he thought that those just couldn't exist. And with that, it seems that he was mistaken. But he was not mistaken in pointing out that that was a feature of the theory. Bohr replied with something... I don't want to say anything bad about it, so I'm not going to say very much about Bohr's reply at all. What I will say is what Bohr said about Bohr's reply. Bohr replied to Einstein's paper almost immediately in 1935, and then he wrote about it again about 15 years later. He wrote about his own reply to Einstein. And in that later piece of writing, he apologized for what he had said in 1935. In particular, he said that it was very difficult to understand, and he apologized for that. And then he did not clarify what he meant and moved on. So, and if Bohr thought it was hard to understand what he was saying, then it was really hard to understand. But Schrödinger, another one of the founders of quantum mechanics, father of the Schrödinger equation, he agreed with Einstein that there was something wrong here, something rotten in the state of Denmark, and so he replied to the EPR paper with a pair of even more famous papers. One of them talking about this idea of entanglement, pointing out that it's a very, very general feature in quantum physics. And he also came up with his own thought experiment known as Schrödinger's cat. And pointed out that when you have a particle in two seemingly contradictory states, like in one place and in another place, entanglement means that you can sort of transfer that contradictoriness to some large object, like a cat that is both dead and alive. And maybe particles can be in two places at once, but cats cannot be both dead and alive. And that was what Schrödinger was pointing out with his cat. He said, this is a problem with quantum physics and we need to find a way to solve it. And strangely, most of his contemporaries basically said, no, there's no problem with this cat. Cats can be dead and alive when we're not looking at them. It's only when we look at them that they have to be one or the other, which is not just a profoundly weird thing to say, but a profoundly vague and questionably coherent thing to say, because you have to say, okay, what do you mean by looking? And all of these problems from the measurement problem rear their heads again. And while some of Schrödinger's contemporaries tried to find ways to deal with this, none of them found a satisfactory solution. This idea of entanglement goes back to the very early days of quantum physics. But it wasn't until John Bell really clarified the situation that people started paying attention to it in a meaningful way. And in fact, you can track how often scientists mention other scientists' papers in their papers, how often they cite those papers. And right now, that EPR paper by Einstein and his two collaborators, that paper is one of the most cited papers in all of physics, but until Bell did his work, it was not very widely cited at all. People didn't really pay attention to it.
Yeah, this can give people hope, I think.
Yes, absolutely.
A number of us who are trying to do important work, and it doesn't necessarily get picked up right away, but it's interesting to hear that some of these papers that sit around for a while later have a very large impact.
Yes, indeed, yeah.
Yeah, and that, the applications that are coming out of technologies enabled by quantum entanglement are pretty amazing and impressive, including ways to build more powerful computers that could do certain kinds of calculations that would take our normal laptops longer than the age of the universe by far. The idea to create methods of communication and encryption that in theory could be perfectly secure.
Yep.
So this is just another example about how basic research into the fundamental nature of reality, even though you might not be able to predict exactly where it's going to lead, can have really, really important downstream consequences that really affect people's daily lives.
Absolutely, yeah. And I would point out, not only is that true, but we don't really know what the full impact of this is going to be yet. And I don't just mean that, there's the technological impact, but there's also the sort of theoretical impact within physics. We don't know what new theories we're going to be able to come up with as a result of this stuff. And we don't know, and we also don't know how these new pictures of reality that we're getting from the foundations of quantum physics will filter out into the wider culture, how they will change the way that we look at the world. There's an example I actually use in my book, and I swear when I wrote this example, I did not know that we would be here recording this podcast at the Arthur C. Clarke Center. But without Copernicus's move of taking the Earth out of the center of the universe, we certainly wouldn't have ever had Darwin taking humanity out from a special place in life and moving it in with the rest of life on Earth in one giant web and family tree of life. And without both Copernicus's ideas and Darwin's ideas about evolution, Clarke and Kubrick would never have been able to make 2001. That wouldn't have happened. And that would have changed the cultural course of history in the 20th century. So we don't know what's going to happen with these things. But the way we look at reality, these pictures about the world that come from science, historically have had enormous impact on the way we conduct every aspect of our daily lives.
Absolutely. And the many worlds interpretation in particular is something that's become even more of a staple in science fiction after the work of Hugh Everett.
Yes.
And that one thing I think that's kind of interesting in comparing it to the Bohmian interpretation is that I would argue that the many worlds interpretation very obviously lends itself to science fiction in a way that the Bohmian interpretation does not.
That is true.
I don't see a pilot wave, Star Trek, the next generation,
I think
coming.
Yeah, I think that's right. I think that the way in which pilot waves could be sort of abused would be to say, they allow for faster than light communication, but they don't. They provably do not.
Yeah, and on that point, many people, when entanglement was first discovered, were very excited that somehow it meant that entangled systems, one particle that's very far away, something you do to it would obviously instantaneously influence the state of the other. This could be used for faster than light communication, and it turns out that it can't, and it doesn't violate relativity. Can you talk more about that?
Well, yeah. I mean, that is something that people got excited about in the 1970s after Bell's work, and you can't do that. Bell proved that you can't do that. It's informally known as the no-Bell telephone theorem, which is kind of great. But yeah, I think that the idea of communicating faster than light would be amazing. It would certainly break special relativity. Special relativity says that if you can do that, here's another great piece of terminology. It says that if you can build something that allows you to communicate faster than light, something that's known as a tachyonic anti-telephone, you can actually send signals to yourself in your past. And that seems to lead to contradictions, so that would be a problem. But yeah, you can't do it. And this is one of sort of the mysteries of quantum physics, and one of the things that a full accounting of the quantum world needs to answer is, how is it that we have these long-distance, instantaneous connections between particles, yet we can't use that to signal? So in pilot wave theory, in Bohmian mechanics, the answer is, the instantaneous connections at a distance are real, but nature ensures that we can't use them. In the many worlds interpretation, it's a little bit less clear what's going on, but at least in some versions of that, what's going on is, there actually aren't the long-distance connections, because if you have more than one universe, that breaks one of the assumptions in Bell's proof. There are other ways of handling this as well. But yeah, and actually the questions of what assumptions go into Bell's theorem are that's actually an area of controversy, because it was something that was misunderstood for a very long time, and clearing up those misunderstandings is one of the things I'm hoping to do with this book.
Yeah, and I'm a little bit biased because this touches on the stuff that I work on, but there are many different assumptions that have been neglected for quite a long time because they were misunderstood, and one of them is this assumption about how free are we as experimenters to make choices for the kinds of measurements that we're making.
Yeah. And
even if it's not a human involved,
right,
how free are our measuring devices
that's right,
to make choices? It turns out that, interestingly enough, one of the features that Bohmian mechanics preserves is the idea that particles can have definite positions and paths through space and time, even when we're not looking.
Yep.
And that at least what the kind of stuff that we're working on has shown is that if you wanted to keep reality, definite positions and paths, if you wanted to keep locality so that relativity is obeyed, you can still reproduce the predictions of quantum mechanics if you slightly relax the amount of freedom suitably defined that experimenters have, or their devices have, in choosing how to measure things for their experiment. And so it's a very subtle and deep issue. And who knows, it could lead to new physics.
Yep.
I think that everybody agrees in the community that quantum mechanics is not the full story. We know that we can't merge it together with general relativity, Einstein's theory of gravity, our other big pillar of foundational physics, and that we don't quite know exactly what that theory is going to look like. There's some candidates like string theory and loop quantum gravity and others. But one of the reasons why I think foundations are incredibly important is that somebody's approach, maybe ours, maybe not, is going to, I hope, lead to a new experiment which will actually allow us to gain some new empirical information that points its way towards a theory of quantum gravity.
Yeah, and I think that one thing that's interesting there is you're saying that, experimental physics has a role to play in figuring out the foundations of quantum mechanics, and I think that's true, right? So the focus we've had so far has been on theoretical physics and the work done by theoretical physicists, but there's a role to play for experimental physics, and there's also a role to play for philosophy.
Yes.
Right, and that's something we haven't come to yet. But Adam, you have some training in philosophy. And in the book, philosophy comes up as a player in the story. I'm in the philosophy department. I work on the philosophy of physics. I'm there in part because I wanted to ask some of these questions within a physics department, and it was not encouraged there. And so I found myself in a philosophy department. But I love it there. I think philosophy is great, and I think philosophy can contribute to this project. How do you see philosophy fitting into attempts to understand the foundations of quantum mechanics?
I love this question, and I will also say, part of the reason I wrote this book was that these were questions I was interested in, and they are not easy to pursue within a physics department, and so writing this book was a way of doing that. But I should make it clear, I do have some background in philosophy. I did an undergraduate degree in it, but Chip, you have a lot more. You're a professor of philosophy. But that being said, I think that a lot of the role that philosophy has to play here is in going after these questions. These questions about what's going on at the heart of the theory. In a sense, there's nothing wrong with shutting up and calculating as long as you don't elevate it into some sort of moral principle. If you say, look, I'm not interested in those questions, I'm interested in applying this new theory, there's nothing wrong with that.
Yeah, that's a personal choice.
Yeah, exactly.
It's not a scientific choice.
Right. The problem.
Like, what should I have for dinner?
Right. Exactly. Like, what should I have for dinner? Yeah. The problem is when you say no. Everyone has to have the same thing for dinner that I'm having.
Right.
I'm having chicken. Everyone's having chicken, and if you don't have chicken, you're not a real physicist. That's a problem.
Right.
I think that the role that philosophy has is in saying, look, we're going to go after these questions. We think these questions are important, and we're going to flag them up as important questions for the physics department and try to help figure out, what possible options are available for them. I see physics and philosophy as engaged in the same enterprise, understanding this world around us, a world that we never made.
And whether people admit it or not, in physics, every theoretical idea starts with philosophical assumptions.
That's right,
and that if you don't examine them, and if you're not sure they're coherent, then you're going to lead yourself and maybe a whole community down a blind alley.
Exactly, physicists engage in philosophy all the time, whether or not they admit that they are, and I think that a great example of this is actually in the way that the Copenhagen Interpretation survived. This idea that you don't need to think about what's going on in the real world is itself sort of founded in what is now a sort of outdated and discredited philosophy of science.
Right.
And this counter argument that you heard me using earlier in this podcast that the theory of quantum mechanics has to be sort of lined up with something in the world in some way, because otherwise how could we explain its phenomenal success, is an argument that comes directly out of philosophy.
Right.
And if somebody thinks I'm wrong, there are counter-arguments to that argument that come directly out of philosophy. I just don't find those counter-arguments compelling. But they are the best ones available.
Yeah.
So the answer is, whether or not you think the foundations of quantum mechanics are important, if you're a physicist, you should definitely be doing some sort of philosophy, or at least listening to what the philosophers say, because it has some bearing on your work.
Thanks, Adam. I certainly agree with that.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.